Hello, my name is Selva Samuel, and in this presentation, I'm going to talk about our work on facilitating connector evolution with architecture-centric development. As you know, the runtime architecture of a system can be described using components and connectors. Components are the computational units and data stores in the system, and connectors describe the mechanisms by which components interact with each other. As a system continues in operation, its runtime architecture might need to be evolved for any number of reasons. In recent years, one important way in which people have become interested in changing architectures is switching a connector with another connector. For example, there is this company called Checkr. They provide background checking services. They have the system that supports their background checking operations. It is essentially a producer-consumer system based on the message broker architectural pattern. Here, the message broker acts as the connector. Initially, they had implemented the system using RabbitMQ as the message broker. However, as they scaled their operations, they found that there was a bottleneck in the system caused by RabbitMQ. So they decided to migrate the system to use Apache Kafka instead as the message broker. The task of connector evolution involves several challenges. To look at these challenges, let us consider this simple example system. It consists of a single producer and a single consumer that interact via a RabbitMQ message queue, and we want to change the system to use Apache Kafka topics instead. The first challenge is that the changes that you need to make to the source code to change a connector are non-localized. Here you can see the implementation of the producer. On the left is the implementation that uses RabbitMQ. The implementation of a connector usually involves performing some initialization, then you exchange data over the initialized connector, and finally you perform some cleanup. All these operations are spread across multiple locations in a file. To change a connector, you have to make changes in all these places. The right-hand side shows the implementation after migrating to Apache Kafka. You have to make similar changes in the consumer as well, and as the system grows larger, you might have to change thousands of lines and hundreds of files, which can be quite tedious and error-prone. So that's the first challenge. Second, data errors may be introduced into the system during the migration process. Here you can see one way that this might happen. The producer in our simple example system just publishes the string hello world. In the RabbitMQ based implementation on the left, the basic underscore publish function that you can see on line 11 is used to do this. The message hello world has been passed as an argument of type string to this function. In the Apache Kafka based implementation on the right, the function send that you can see on line 6 is used to publish the message. Here you have to pass the message as an argument of type bytes, and this is done by adding the prefix b. So if developers are not careful while making this change, the published data would be corrupted after the migration. Third, behavioral errors may be introduced into the system during the migration process. One way this can happen is that changing a connector might require performing complex refactorings. For example, in this producer-consumer system, receiving messages in the consumer involves using a callback function in the RabbitMQ-based implementation. But you have to do polling in Apache Kafka. Previous studies have shown that developers can introduce bugs when doing refactorings like these, and the chance of introducing errors increases as the number of refactorings you have to make increases. So those are the three challenges with connector evolution. Based on these three challenges, we have three goals for our solution approach. First, we want localized changes. Changes to be made for migrating from one connector to another should be restricted to as few lines as possible in as few files as possible. Second, we want data uniformity. The data that individual components read from and write to each connector must remain the same before and after the connector change. And third, we want semantic equivalence of individual components. There should be no change in the behavior of individual components, provided that The data read from and written to each connector by the components remains the same after the connector change. Now I will give an overview of our approach. We have implemented our approach in a language that we have designed called Wyvern. First, notice that the reason why you have to make non-localized changes when migrating a connector is that existing programming languages do not have an abstraction mechanism for modularizing connectors. So in Wyvern, we have introduced a language mechanism for specifying connector abstractions. The connector abstraction mechanism is reusable and component agnostic. What that means is that the abstraction only specifies the semantics of an interaction and can be used to generate code using metaprogramming for any components that need to be tied together using the connector. So then, in the component implementations, you cannot include code for connector implementation. Instead, components can only interact using interfaces. Now secondly, notice that in existing programming languages, developers have unrestricted access to libraries that can be used for implementing connectors. So they can easily bypass any connector abstractions even if they were available and implement component interactions directly by using these libraries. In our approach, we prevent this by associating capabilities with libraries that can be used for implementing connectors. Component implementations do not have access to these capabilities, so the developers cannot use these libraries in the component implementations. Only connector abstractions have access to these capabilities. Now, if component implementations cannot include connector code, how do you specify which components interact with each other? For that, we use an architecture description. So the compiler takes in these three sets of artifacts: architecture description, connector abstraction, and component implementations, and generates the executable system. Now let me show you what this looks like concretely in our example producer-consumer system. First, let's look at the architecture description. The architecture is specified using components, connectors, and attachments like in most ADLs. Here you have two components, producer and consumer, and one connector, RabbitMQQ. Components have ports which have an associated interface. Connectors have attributes which are properties like hostname and queuename which must be configured to set up interactions between components. Now, how are components implemented? Components are implemented as modules. Modules in Wyvern are similar to functors in ML. Essentially, you can think of them as a function that takes in 0 or more arguments, each of which is a module instance of a specified type, and a module instance is returned as a result. Here you can see the modules for the producer and the consumer. As I mentioned earlier, we restrict components from accessing libraries that can be used to implement connectors. So they are implemented using only interfaces. Finally, how do you specify the connector abstraction? For that, you have to define a type and attach metadata with the type. The metadata is used for metaprogramming and contains code that is executed by the compiler. We have two standard functions in the metadata. One is check port compatibility, which can be used to check if the components being attached have compatible interfaces. The other one is generate connector impl, which is used to specify the code that should be generated to implement a connector's functionality. Developers can customize these functions depending on the requirements for the system they are implementing. Now, how do you change a connector? Basically, you have to change the architecture description to specify the new connector that you want to use. Then, you have to supply the connector abstraction for the new connector. After you have done this, you can compile the system like before. Concretely, in our producer-consumer example system, you will have to use the Apache Kafka topic connector instead of RabbitMQQ. This is done in lines 5 and 14 here. And you also have to supply the connector abstraction for the Apache Kafka topic connector, which is this type and its associated metadata. So how does our approach meet our goals? As you saw that in our approach, how components are tied together using connectors is not specified in the implementation, but only in the architecture description. Moreover, since the architecture description is specified at a high level of abstraction, so the changes are limited to a few lines. So the goal of non-localized changes is met. Since the component implementations do not need to be changed, so the goals of data uniformity and semantic equivalence of individual components are also met. We evaluated our approach on a ROS-based robotic system. ROS has two versions, ROS 1 and ROS 2. Since ROS 1 lacks support for security and real-time features, ROS 2 was developed. Because ROS developers have ended support for ROS 1, so existing ROS 1 systems have to be migrated to ROS 2. We use the Turtlebot 3 teleoperation system shown here for our evaluation. ROS systems consist of independent components called nodes. Here we have three nodes, Turtlebot 3 teleop keyboard, Turtlebot 3 fake node, and robot state publisher. In ROS, nodes can communicate using a variety of primitives. You have topics, which is a publish-subscribe mechanism. You have services, which is an RPC mechanism, and so on. Here, the three nodes are connected together using a number of topics. This system has already been converted to ROS 2 by ROS developers. Here, you can see the files implementing each node in the ROS 1 and ROS 2 versions, and also the number of lines that they had to change in each file. As you can see, in total they had to change over 60 lines across 7 files. We rewrote the system in our approach. Here you can see the partial architecture description of the Turtlebot 3 teleop system in Wyvern. The architecture description consists of 39 lines. In the initial implementation, we used ROS 1. You can see this in lines 18 and 27. Changing this to ROS 2 just required changing to the appropriate connector. So we just had to modify 4 lines in the architecture description to migrate the connectors in the system from ROS 1 to ROS 2. As I mentioned earlier, this fulfills the goal of localized changes. And since the component implementations are not changed, goals of data uniformity and semantic equivalence of individual components are also met. So to summarize, I described the challenges involved in connector evolution, non-localized changes, potential for data errors, and potential for behavioral errors. I showed how our approach can mitigate these challenges. Our approach involves integrating architecture specification with code. We have shown how the programming language mechanisms of capabilities and metaprogramming can be used to achieve our goals. That concludes my talk. Thank you very much for your attention.